EIEIO Games, the guy that brought you a million checkboxes, wrote down every single UUID. My guess is that, I like the joke. I've been struggling to remember all the UUIDs. There's a lot of them, so I wrote them all down. And I've never actually, I've seen this thing pop up like 9,000 times on Twitter. I haven't actually looked at it. And so here it is. It's just an in-ordered list, I assume. It feels very, very good. I like how it says, well, only the V4 ones. That's also very funny. Okay, hold on. Is there like a lot of elements here, or is is he doing some fancy? I assume he's doing some fancy footwork because it just looks. It was obviously too smooth. Yeah. Okay. And so it's just JavaScript scrolling, and the scroll bar up here is just that way, and it's just updating them really, really fast. Okay, that's what I figured it was doing. That's fantastic. This is beautiful. Absolutely beautiful. I found my government UUID. Is there a website that leaked all the CVV codes? Oh my gosh. It just is unstoppable. I bet yeah, it's just a nice little list. This is really, really good. You'll notice that there's no DOM updates, right? The DOM updates exist right in here, I assume. There you go. I wonder how he did this where it looks randomized this way, but then it's counted right here. I wonder how that algorithm worked. Because, like, you know, you could do search. I feel like I understand how the search works. That feels like it's pretty simple to understand how the search works. Oh, that's not how I would have done it. Interesting. How many occurrences are there? Crazy. Okay, anyways, this is good. Okay, so I want to know how this thing works, okay? I guess that it's finite, like IP addresses. Of course it's finite. It's 128 bits. I've been struggling to remember all the UUIDs. There's a lot of them. So this week I wrote them all down. You can see my list at everyuuid.com. The site looks like this. UUIDs are displayed in a random-ish but consistent order so you can quickly search for the ones you like. That's absolutely beautiful. That's what I've always wanted in life. You know, I do agree. It is very hard to remember them all. I mean, it starts at 0, and it goes for a long time. All right, but having all, is it really that much? Is that 128 bits? Is 128 bits this? Is it really that long? That's a big ass number. Possible values made it way harder, right? Yeah, has 128 bits. UUID 4s have 4 reserved bits for the version and 2 or 3 bits for variant. I chose the 2-bit variant, which left me with 122 bits of entropy. Okay, that's a lot of bits. So I think the final implementation here is pretty interesting. Let me tell you about it. The challenges. The problem had a few major challenges. Browsers do not want to render a window with that is over a trillion pixels high. So I needed to handle scrolling and rendering on my own. You know, who would have guessed? Who would have honestly guessed that browsers would not want to handle a trillion pixel landscape? I think this makes sense. I didn't want to generate UUIDs in order from first to last. We all know the good UUIDs are in the middle. And so I needed a way to generate UUIDs that ensured that I generate them all once. Yeah, there's some sort of seed, effectively as a seed to walk through all this. I was handling scrolling and rendering on my own. Control F didn't really work for search. I wanted to search through every UUID, not just the ones I could see. So I had implemented that too. Well, the thing is he must not have technically implemented it that well. Because when I go like this, look, we can actually go, you'll notice that I'm going through the whole list right now. If I hold it, I just went through the whole list. Now I went back up to the top, and I'm still back through the whole list. Because if you really think about it, a UUID can end with AABB, and then the amount of variations right here would just be an enormous amount, right? Because if you had 122 bits of entropy, with AABB, you were effectively using, what is that? That's 16 bits, so do a little quick 16 minus that thing, so you have 104 bits left. I mean, that number is infinitely large, right? So this one single spot would have an infinitely large amount of them. They're just random though, right? What do you mean they're just random? They're randomly ordered. But I can go through the whole list, right? See, you can see it go through the whole list right here. See, now it's back up at the top. Like, I should never be able, I mean, technically, I should never be able to do that. Okay? Hey, I'm just saying, technically, there'd be too many. I originally figured I'd make a very, very tall div, only render the UUIDs that I could see. This is the approach that I took with 1 million checkboxes, and it worked great there. The idea is creating trillions of DOM nodes is expensive. I like how that's just said so casually. Yeah, doing a trillion of anything just felt really expensive, so I didn't want to do it that way, but having a very high scroll position isn't. It's still a single number. So you make a div that is tall enough to contain all your elements and then just render the ones that are close along with the buffer. But unfortunately, browsers have a maximum scroll position. I'm not entirely sure what that is across all browsers now, but it seems like it's probably stored as a 32-bit int in at least some browsers. And even if it was 64-bit int and we're displaying all the UUIDs with the height of 1 pixel, we'd still need an order of magnitude more scroll space. Interesting. That is a problem I did not see coming. Like, out of all things to think about, this is it's just not the one I thought. What are the limitations regarding height in pixels of an HTML page? If so, what are the factors affecting the maximum? Is it browser specific, especially IE7? That's a crazy question. This is such an old, how old is this? This thing got closed 12 years ago. Still being worried about IE7 in 2012? That is just nuts. Oh, that is just nuts. 2012, still thinking about IE7. Just insanity. My solution was a bit finicky to implement, but conceptually pretty simple. Don't do any real scrolling. Fix the height of the page to the height of the browser. Store the virtual scroll position in a big int. Update it whenever the user performs a scroll-like action. Render UUIDs based on the scroll position. If we're at position 1000, then render UUID 1000, etc. Yeah, this makes sense. Okay, this was a finically large because there's a lot of stuff that browsers do for you when it comes to scrolling. So if you want a good user experience, there's a lot of stuff that you need to remember and to re-implement. Yes, scrolling sucks. You need to handle mouse wheel and touch events yourself. You need to find all the platform-specific hotkeys for scrolling and add those. You need to add your own scroll bar. And if you want nice scrolling animation, you have to add that to yourself. None of that is hard. There's just a lot of it. Yes. 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 Oh, man, I had to do my own scrolling one time, and it's exceptionally... There's just so many things that go wrong when you do your own scrolling. It's shocking how many, little fun facts you'll end up discovering along the way. It ain't worth it. It's not worth it. For example, here's my hotkey for handling code. I'm sure you've missed plenty of stuff. Hotkey for handling code. Switch true. Handle key and prevent, arrow down. Animation with delta. Handle, let's see, arrow E, up. Space. Space without shift key. Page down with command key. Page up. No, that's home, end, arrow up, arrow down. What were the other ones? Oh, arrow up, arrow down with command key. Why don't you at least put them near each other? Hey, code review. Hey, knit. Arrow key down should be near arrow key down up top. Okay, that's a knit. I'd like to see that moved up to the tippity top, buddy. No Vimium, Sag. The only thing I ended up using Vimium for was really just came down to me effectively just pressing G, D, and U. And I was just like, am I really getting anything out of this? Because I'm still using a lot of that. Because even when I pressed F, when everything lights up as clickable, it's just like, that's not that great. You know what I mean? They already implemented Vim motions in the PR. Good. That's what we're talking about. So this got me to a list of UUIDs. I add some other important functionality. For example, if I see a UUID that I wanted to be able to favorite it, to come back to later to, or to copy it to my clipboard, and that gave me something like this, dude. Favorite a UUID is actually unhinged behavior. That is the most... I know, there's a cat. There was a black cat. Did you see the black cat? Right? It was a black cat. This is the most unhinged behavior, is favoriting a UUID. That's crazy. That's crazy talk. That works, but the UUIDs are displayed in super obvious order. Scrolling through the list should be exciting. I want to see this and not that. Exactly. We can do better. Ordering. I assume they used Mulberry 32. Some sort of... there has to be a random order that eventually you can walk through the whole list. Showcat, the black one. You can't just grab the black one, okay? The black one's all slanky and slinky and slunks right out of the door. Challenge 2, ordering. I want to display the UUIDs in an interesting order, so I came up with the following constraints. There should be no distinguishable pattern to the UUIDs displayed. We should display every UUID exactly once. UUIDs should be displayed in a consistent order. After all, it'd be disappointing if you scrolled through every UUID and realized that you hadn't seen one. And it'd be very hard to show someone a UUID that you found if you couldn't scroll back to the same spot to find it. Yeah. So we need so we need to map our integer indices to UUIDs in an interesting way. How do we do that?
Welcome to Costco.
I forgot to turn off alerts. Sorry. I will do better. Thank you, Pitwack. Appreciate that. I'm curious what these. First idea was the linear congruential generator. I've never even heard of a linear congruential generator. Is it to generate an interesting path? Is that what this is? Okay, it's to... Let's see, is an algorithm that yields a sequence of pseudo-randomized numbers calculated with a discontinuous piecewise linear equation. The method represents one of the oldest and best-known pseudo-random number generators. Huh. Well, that's kind of neat. The LCG generates random pseudo numbers using the following formula: x plus 1 equals a times xn plus c mod m. That is, to go to the next term, you need to take the previous term, multiply it by a, and add c, and take that to the mod m. For reasons that are beyond me, if m is a power of 2, m and c share no common factors. A minus 1 is divisible by all prime factors of m, and a1 is divisible by 4 if m is divisible by 4. You will generate all values below m before you get any repeats. I would just like to say, Prime mentioned, I knew it. We are in. We're so in. We are so in right now. You don't have to understand any of it. You just got to understand that there it is right there. Let's go. We're in. We are so in. Pre-read, pre-reacted to. So this seemed like a good fit. We can set m to that number and choose any odd number for c, and easily pick an a that is above or that is one above the number divisible by 4. But I quickly ran into problems. Oh, those are not beautiful. That is not beautiful. This is not beautiful right here. Yeah, because I can tell. Okay. Because even if you jump forward a little bit, even by a lot, it's still very similar in the grand scheme of things. Oh, no! There's a table of UUIDs generated using 9 for A, 5 for C. The UUIDs sure don't look random, and that makes sense. If we wanted to see anything but zeros for the high bits of the second UUID that we generated, we need A times C to approach 2 to that number. So I needed to... Let's see. So they need to each be close to that number right there. Those are big numbers to multiply together, but computers are fast these days. But that gets tricky when generating later terms. While there are ways to skip steps with LCGs, that is to generate the LCG for a million inputs without generating 99999 prior calculations. I found it hard to get the math working consistently with large constants because the intermediate steps were so big. Oh yeah, that makes sense. That makes perfect sense because that's the whole problem is you cannot have a formula that relies on the past version. Because then if you tried to do any sort of scrolling, it'd just be like, not gonna work out. In an environment such as a video game console, taking a small number of high-ordered bits of an LCG may well suffice. The low-order bits of LCGs, when m is a power of 2, should never be relied on for any degree of randomness whatsoever. As I was working through the problem, I noticed that the Wikipedia said the low number of bits in LCGs when m is a power of 2 should never be relied on for any degree of randomness whatsoever. So I decided to pivot. This is math I don't ever do this kind of math. So I wanted to add more entropy to display to the displayed UUIDs, but to display each UUID exactly once, mathematicians would say I wanted a bijective mapping. That is, for each index to be mapped to exactly one UUID and vice versa. I find a bijectivity hard to reason about. Facts. Dude, the guy's correct. I knew my original mapping was bijective. It's clear that index 0 maps to UUID this right here, and vice versa. But how could I tell whether I was preserving the bijectivity when adding entropy? Could I take my index and add a constant to it? Could I multiply each index by 1,000? A bijective function or one-to-one correspondence between two mathematical sets is a function such that each element of the second set, the codomain, is the image of exactly one element in the first set, the domain. Equivalently, a bijection is a relation between two sets such that each element of either set is paired with exactly one element in the other set. You know, I haven't read things like this in a long time, okay? It's been a long time since I've been reading about bijections. All of a sudden we went into domain math. I know, that's just not math I'm used to. A function is bijective if and only if it is invertible. Classic invertible function. That is, a function x to y is bijective if and only if there is a function g y to x. Classic. That makes sense, right? If it's a one-to-one mapping, if one can map to the other, then therefore the other should be able to map back to it. If you think about it, that makes perfect sense. You just lost 200 viewers? Absolutely. This is getting way too intense. That's fine, though. But eventually, I stumbled on an observation that is probably obvious to many of you, but blew my mind. As long as I could always reverse the steps that I took, I had preserved bijectivity. Type 1 in the chat if that was obvious. You know what I see right now? I see a lot of people lying right now, okay? I see a lot of people lying right now. It's kind of crazy. Kind of crazy. The way I think about it is I have a function. It takes an index and returns exactly one UUID. It always returns the same UUID for the same input. The way that I add entropy is reversible, which means that I can take a UUID, reverse the steps that I took, and recover the index that I generated it. Having a duplicate would require two indices to have the same UUID, which would mean that I could never, that's a weird to have a bullet point right here, which would mean that I could never, or I couldn't recover one of those two indices by reversing the steps that I took. But we said we could always do that. Maybe this is silly, but framing the problem as come up with a function that looks like it adds entropy but is reversible was a lot easier for me to think about than preserving bijectivity between these two sets. Yeah, that sounds, it sounds easier. So this gave me a new approach to try to write down with some precision. We're given 122 bits of input for index 0. All of those bits happen to be 0, but they're there. We can do anything we want with those bits to add entropy as long as we end up with exactly 122 bits. We need to create UUID. We can take our final 122 bits and recover the original 122 bits. So by multiplying a large number, multiplying by a large number was out. And since that would increase the number of bits, but XOR was very much alive. And since you can XOR a number with some other number twice and you get back the original number, yes, I love this. Except for you can't XOR yourself. If you XOR yourself, you can never recover that number because then it's all zeros. It's a sad day. There was this time that I had to, I tried to race somebody. Chat, in fact, was the somebody. If I could write a linked list with only using XOR to swap the nodes. And one of the nodes was like a 0 node. It was just 0, and I lost all the data. All the data went bye-bye. Don't do it. It's not worth it. Feistel ciphers. So I wanted to preserve the number of bits that I had and some entropy in a reversible way. A cipher seems like a good approach. The whole idea of a cipher is to scramble text in an interesting but totally reversible, if you know how. If you know kind of way. I am sure there's a lot of good options here, but I settled for the Feistel cipher because it was easy for me to see how it would satisfy my constraints. Feistel ciphers are cool and very elegant. The basic idea looks like this. I like ciphers. Ciphers are exciting. This isn't quite valid code, but it's good enough. Okay, so we have these constants, big numbers here. Produce a ciphertext. Left, unscramble. What is it? What is this division right here? Why is there two divide signs? Is this some sort of? Is this Python? Python is that like floor divide? It's floor divide, isn't it? Floor division? Yeah. Okay. That makes sense. Okay, so we have this one, unscrambled. We get left, we get right. For constants, we get a seed round function. Right round. Seed is the function of the right. New right equals this thing. XOR those two together. Left equals right. New left side of the old right side. Left equals new right. Add those together. I don't even know what just happened. Honestly, I didn't see what happened there. This is why he this is what he's implementing right now. Okay, so this is the one. Oh. It mixes it up with an XOR and then swaps the two sides. And then to undo it, you just effectively re-swap the two sides and re-XOR. Is that effectively what's happening here? All right, that is split your input into two chunks several times in a row. Feed the right chunk into the left that produces some interesting value. XOR that output with your left chunk and make your new right chunk. Make your new left chunk equal to your old right chunk, and then smush the chunks back together at the end. And that's really cool. Let's see, and what's really cool about this is that it's reversible for any round function, as long as the round function is pure. I think there's probably a zero problem somewhere in there. Like if you're there's something in there that probably gets goofy if you accidentally hit like the same number twice and then you'll just zero yourself out. That was originally confusing to me. Why is it okay for round function to be basically anything? It can do something silly like always return run. To see why that's okay, we can look at the steps to reverse the Feistel cipher. All right, so we get left as the old one, then we undo it, and then we undo all these things and we kind of walk it backwards, right? Pass, same as above. The trick here is that we can always recover our seed because the left chunk of our current iteration. And from it, we can always recover our old left chunk because XORing something twice produces the original input. And that means that if our round function always returned 1 and something's, let's see, equally silly. Our data might not be mixed particularly well, but it would still be recoverable. Okay, I implemented the Feistel cipher and tweaked my round function until it scrambled my UUIDs in a satisfying way. That was pretty straightforward. My round implementation suggested by Claude is a bunch of bits, shifts, and XORs with some multiplication mixed in. Nice. That is so many big ints. Big ints are just not fun to work with. That's great. Okay, hey, nice job. But then I needed to take my scrambled bits and turn them back into UUIDs, and that was surprisingly tricky. Aside, bit twiddling is hard. Bit twiddling can get really hard if you goof up. We didn't care about generating valid UUID v4s. We just generated a 2 to the 128. Yeah, okay. And scrambled them, converting the resulting bits into a hex string, and interspersed some dashes. And let's see. But it'd be heartbreaking if someone found a UUID on the site, only to realize that it didn't correspond to the v4 standard. A UUID v4 must look like this. Let's see. There's the randomness, right? Okay, there's the 4. And there's the V. The V is the, let's see, the 2 top bits here are 1, 0. Valid values are 8, 9, A, and B. So you have to do a bit of constraining, right? It's a little awkward to take our 2 chunks of 61 bits and map it into an available bits here. We need to do something like this. Yeah, it can get real, like, bit smushing can get really annoying. There's a lot of ORing and all that fun stuff that you have to do. Let's see. I'm sure that someone more comfortable with bit twiddling would have come up with a better approach here, but I couldn't think of a solution other than carefully twiddling all the bits into place. Let's see. Left initial. All right. We're going to, yep. Okay, so we just effectively, this just means strip off the first 61 bits. Right initial is going to take the big int index. We're going to take this 1, we're going to shift it into the 62nd place. Then we're going to -1, which makes it all into a bunch of 1s. All right, for those that don't know what this does, that's really, really simple one. A really easy way to produce a whole bunch of 1s is to take a power of 2 and -1, right? So imagine you did something like this. Say, instead you take 8. 8 minus 1 equals 7. How do you represent 7 in binary? Well, you need a 1, you need a 2, and you need a 4, right? So if you do 16 minus 1, exact same thing, right? So that would be, or 16 minus 1 equals 15. I couldn't really write that. And so exact same thing. 15 is just simply 7 plus 8. So it's just one more bit. It's just right there. It's just right there. This guy twiddles. Oh, I've twiddled. And so all he did is he just split the 2 sides, right? Shifted everything over on the far end, on the most significant side, and then effectively just masked out everything on the most significant side. That's what this does, masks it all out. All right, left and right, run Feistel, result big int. All right, we're going to OR in a nice left 13, shift big right this one. I always use parentheses. A lot of parentheses for these ones, just so I wouldn't goof it up, because this ordering gets really tricky. I don't even know what's happening. First 48 bits come from the left, 13 bits remaining, right 61 bits remaining, total 48 bits used. Classic. Just a classic. Okay, so you're going to shift off 13, yep, which makes it 48, and then shift that over 80. This looks so easy to screw up. 4 bits for version. All right, nice, beautiful. All right, I think I've seen enough bit shifting, but we get the idea. Just shift each one. I don't know. I don't know if I could have done it any better, because I would have just had to shift each step in. I think this is completely reasonable to do. This was a bug prone for me. I am bad at bit twiddling, and and an area where LLMs seem to really struggle. Maybe because the process is mathy. I had to redraw everything to get it working, but eventually it worked, and it gave me a very nice list of random looking but consistently ordered UUIDs. Beautiful. Look at that. Look how random that looked. Challenge 3, search. When shuffling the order of displayed UUIDs posed a problem, how could we find the UUIDs that I liked? Back when the UUIDs were more ordered, I could at least try to scroll to the right area to find one, but that didn't work now, so I needed to add search. Because our mixing function was reversible, adding search was for a specific UUID was pretty easy. We just had to take a UUID, unscramble it to retrieve the original index, and then jump to that index. Yeah, but you don't list them all, okay? When you search, you don't find all the UUIDs. Are you trying to sell me some snake oil here? So I added a little search widget that did just that. But that definitely wasn't enough. Search function should be able to search for substrings. Full text search. The next step was also pretty straightforward. I knew all of the UUIDs in view, so I could easily add full text search over them. And I could extend that buffer to include UUIDs above and below where I was currently looking at to search over to. Okay, beautiful. let's see. And this is the spot where you could wonder why the UUID spec authors thought we needed so many UUIDs. I couldn't make those buffers trillions of items large to hold all the UUIDs. That's too much RAM. I needed to take a different approach. What do we do with search strings? I couldn't search over all the UUIDs directly, but maybe I could take in the search string and then back out some UUIDs that fit it. Something like this. Take the current search string, find all the places where the search string could fit within the UUID, choose one of those places, and fill the surrounding digits to make a valid UUID. Okay. That's reasonable. It didn't do all of them. A little sad. It's a little sad that he didn't list out all of them. I would have personally liked to see all the UUIDs, but I get it. Let's see. For example, if the user typed a string A, it could go into 31 positions in the UUID, and there are 32 characters. But let's see. But one must be a 4. But A could only fit into a single position since there are more than 4 digits. So it must go into the first or last grouping, and a trailing. And a trailing dash, so it can't go in the last grouping. So it must instead go in the last 5 characters of the first grouping, followed by a dash. Maybe it's just because I was tired, but I massively overcomplicated this problem to start. I thought I needed to do something like split the search string on this into chunks, analyze each chunk figuring out where it could go, long chunks must go first or last, use that to determine which digit we still need to fill in to generate the valid UUID. I went in circles, throwing away tons of code that looked like this. This is just so much code for search. This is such a silly problem. I love how doing unuseful stuff like this, you can learn so much. It's true. Dude, it's very, very true. If any takeaway from this is just you learn a ridiculous amount of things by doing something just completely not useful. One theme of this project was Claude really struggled with what I was asking it to do, and that was certainly true here. Claude was also confused about the problem as I was. I still think I haven't got it quite right. I can see some inconsistencies in my implementation versus the rules you laid out. Would you like me to point out what I'm still missing? I'm the LLM now. You are. But at some point, I took a step back and realized there was a much simpler solution. Since we want the user's search string to appear verbatim in any UUID that matched, we can simply take it as their input. We could ask the input string to go at the start of the UUID, ask, could this string go in the second character of the UUID, etc. Visually, it looks something like this. Yeah. So in my head, this is what I was wondering about. Like, why not just literally search through it and just do that? Dashes in the current search must be in the right spot. If a search character overlaps with the version character, it must be a 4. Let's see. It must be a 4. And if the search character overlaps with the variant character, it must also be a 8, 9, A, or B. Generating UUIDs. The search string processing gave me a set of valid patterns. Those patterns would look for. Oh my goodness! I can't read. The search string processing gave me a set of valid patterns. Those patterns would look like this for the string, for AA. Yeah, beautiful. What do we do with those? Well, we want to do something like feed those patterns into our unscrambler, determine the bits we would need to set in our input index in order to output the pattern. Find the index closest to the current position that has those bits set. Now, clearly, we can't just feed those patterns into an unscrambler as is. They're not valid UUIDs, but that's the idea behind what we'd want to do. I just don't understand, like, once you find a valid pattern, there's effectively an infinite amount of things you could generate around it. So how do you choose how many do you do in one position? Because that's the thing. Because when you do the search, what I thought was really interesting, when you search, notice that it goes all over the place. So how did he give like a nice like random feel to the search placement, even though it's clearly not all of them? It's not infinite though. Yeah, you get the idea. What would we do with those? Well, we'd want to do something like this. Like it would take what would be a perceivable infinite amount of time for us to generate all those possibilities. Well, what we want to do is something like this. Feed those patterns into our unscrambler, determine which bits we need to set for our input index in order to output the pattern. Find an index closest to our current position that has the bits set. Now, clearly, we can't just feed those patterns into our unscrambler as is. They're not valid UUIDs. I've already read this, but that's the idea behind it. And it's here that I hit a wall. The dependency graph for any bit spit out of our cipher was wildly complicated. At first, I thought I could fix it. You can't fix it. This by using a different scrambling technique. Maybe I could change the semantics of my cipher or use a known bad crypto algorithm to exploit its breakability. But those ideas were fundamentally at odds with my goals of presentation. For UUIDs to appear randomly ordered, I needed each input bit to affect every output bit. But to reason about the dependency graph of a bit effectively, I needed each input bit to only affect a few output bits. Anything I did to improve one problem made the other problem harder. I've never done any of these things, and it reminds me of like being at DEF CON when we did a bunch of the gold bug problems, which is just a bunch of Cipher style problem taking apart. I was an absolute rookie in those things. But at the same time, this is super cool. Yeah, that's why I definitely did not earn the nickname Caboose. Okay, I do not have a nickname, and it's not Caboose. Anything I did to improve one problem made the other problem harder. Here, I was left with a feeling that if I had a better understanding of cryptanalysis, I might be able to make some headway. But getting the MVP of this project out the door seemed too valuable to divert into studying for that long. People need to browse UUIDs, so I punted. The solution was pretty simple for search. Just take the pattern that I generate while analyzing search strings, repeatedly fill in the remaining digits to generate valid UUIDs, took the best ones, the one closest to the current position. Oh, that's pretty good. And this works pretty well. It's not perfect, but it certainly lets you cycle through a large set of matching UUIDs. Yep, that's pretty good. Okay, that's pretty good. Just good enough. I can accept it. I'll accept your relinquishing of not showing me all of my UUIDs that have AABB in it. Missing features and wrapping up. Flaws of the UUID spec aside, I'm glad I finally have all the UUIDs in one place. There are a few things that I think the site is currently missing. Having more social features would be really... Has anyone ever said that? I'm shocked. Honestly, I'm shocked he did not say having AI would have fixed this. Maybe you could see the UUIDs your friends have favorited so that you could use those UUIDs too. Or maybe the site could feature trending UUIDs that are particularly popular across the world right now. And of course, I'm still very curious whether there's a crypto analysis approach that that lets me achieve more effective search over a randomish ordering of UUIDs. I'm going to do some more reading. But with all that said, I'm very happy to launch the site in its current state. I hope you get as much utility out of it as I do. Dude, trending UUIDs just sounds so cursed. Absolutely beautiful. This is such a funny project. This is such a funny project. And think about how much has been learned and like acquired from this ridiculousness. It's absolutely ridiculous. But if only we had a way to identify all the UUIDs so we can keep track of which ones are popular. Maybe each of those should have some sort of universal, unique way to identify them. I like where this is going. Now make an NFT out of all those UUIDs. Do the greatest NFT scheme of all time. UUIDs. I wish I had this level of autism. It's a level of autism that is unknown to the average person. It's true. It's true. Not many people can achieve that level. I'm trying to figure out what he means by all the UUIDs. It just means all the numbers that exist between 0 all the way up to 2 to the 128. And then there's obviously some rules, like you said. There's like a version in one of the places. Then there's also another thing, some 8, 9, A or B in another place. And so there's some basic constraints. And so it ended up becoming 2 to the 122 as the valid set of random UUIDs. So he generated all those from 0 to this. So he tried to make a search so it'd go to the next closest one. Yeah. Effectively, even to us naughty oddies here. Is that Dan Vale? What the hell does that even mean? He's a little crazy. Slander is not What does that even mean? I don't even know what that means. Hey, the name is this guy. I wonder what he does for his job. He makes funny projects though. He makes a lot of funny projects. His last project was really, really great, which was the 1,000,000 checkboxes. And that one had Python got owned by that one. Went to Go, loved his life. That was fantastic. These are just bizarre projects. Again.